All right, so let's get to the last part of this lesson. The last part of this lesson is about energy diagrams or enthalpy diagrams. And I've got an example of each type of energy diagram here, and we're going to look at how we can use our understanding of potential energy, because that's what they're trying to show here, on our example with the gas can. So we said the gas in the can has a lot of potential energy, and it has potential to turn that energy into heat and potentially kinetic energy. Well, if we imagine what's happening here, and it's always important to kind of draw yourself a scenario of which way the heat is flowing, because it will help you figure out which diagram is correct. So if you imagine that you're standing here and this gasoline that's in this truck is undergoing a reaction, and the type of reaction it's undergoing, of course, is a combustion reaction. This is the formula for gas. And if you remember something about combustion reactions from first semester, that gas will have to react with oxygen and it will make CO2 and water. These reactants will turn in to these products. When they do that, a lot of heat, it looks like to me, a lot of heat is going to be coming out of this truck headed towards you. You're going to feel a lot of warmth. To you, Q would probably be positive because that warmth is coming towards you. But that's not the perspective the truck will have, right? The truck, its energy, I was going to say Q here, would be negative because the heat is leaving it. Now, you know with reactions we typically write delta H, but same thing. So the heat's going to be leaving it. Now, I want you to think of what that's going to do to the energy of the chemicals in there. Let's say we have reactants. There are the reactants and there are the reactants. What an energy diagram is trying to show you is, are the products higher in energy than the reactants, or are the products lower in energy than the reactants? Well, if the heat energy is leaving the reactants, imagine if energy was leaving you. You would feel lower energy. So I think that the products, when the reaction's done, are going to be lower in energy than the reactants. I think B is a better diagram for this particular case. And the reason is because since heat is leaving, this is an exothermic reaction. And in an exothermic reaction, let me spell it right. Since heat is leaving, the products are always lower in energy than the reactants. So that's what an energy diagram is trying to show us, is it's showing us the potential energy of the reactants and products. And if we can figure out if the chemicals, and remember, it's always important to think about the chemicals here, are gaining or losing heat, we can tell which diagram would be the right one. While we're here, let's look at some other things. Do you see, so I think it makes sense that on the y-axis there's potential energy. Kind of like, if we're keeping track of the potential energy of a roller coaster, right? Down here it says reaction progress, which really doesn't mean anything. They're just saying reactants turn into products, so this is at some time later. It's not really a mathematical thing that they're explaining there. Let's look at another one. Well, actually, one more thing I want to talk about before we get to another example is you can think of these sort of diagrams an awful lot as kind of like skiing. If you've ever been skiing or snowboarding, you can imagine that if you were skiing down the hill like this person, right? You were skiing downhill. You started up here at a place of high potential energy, and you were skiing downhill to a place of low potential energy. That would be a pretty easy process. You wouldn't have to put any energy into it. That's kind of what exothermic reactions are like, right? They happen fairly naturally. You don't have to do too much. But if you were a person who had decided, like say this person was walking over with her snowboard and she was going to walk up the hill from low to high, that's like walking uphill from low potential energy to high potential energy. Well, you're going to have to put a lot of energy walking up that hill into this process. So you're going to have to put energy in. That's an endothermic process. It takes a lot more work to do that because you have to add energy into it. So I think ski hills or something like that, you can imagine yourself mountain biking up it if you wanted to. But those processes, endothermic processes, they tend to not happen as naturally as exothermic processes do. All right, let's look at one of our examples from the very beginning of this lesson where we poured in this white powder. I think this one was ammonium nitrate, but it doesn't matter. Let's find out what happens here. All right, I see it. This is the one where the temperature went down. So we were adding ammonium chloride in, and this is the reaction it was doing as the temperature went down. We have the reactants over here, and we have the products over there. Now, if we stop and think about what was happening with this, because the temperature was going down, that means that these particles in here, and since it's all already mixed up, I'm going to draw a red dot representing the particles. The temperature was going down. The water itself, let me write water, was losing energy because the temperature is going down. Remember, the thermometer is monitoring the water. Because the temperature is going down, the water is losing energy. I think energy is going away from the water into the ammonium chloride particles. So energy is flowing away from water and into the ammonium chloride. The ammonium chloride is gaining energy. Its Q would be positive, or since it's a chemical, we'd say its delta H would be positive. Now that I have the diagram right, I can come over here and figure out whether number 1 or number 2 is the right diagram. And I want you to look at the energy of the reactants versus the energy of the products in both ones. And based on our drawing, I want you to make a prediction. Is diagram number 1 or diagram number 2 the better energy diagram? Well, here's how I would explain it. Is if the water's getting colder, that means the water's losing energy. The particle's gaining energy. If the particle's gaining energy, then that means the reactants are gaining energy. And so the products have to be higher in potential energy because they're gaining energy. That's why they're higher in energy. You can think of them as sort of like these are the kids ate some candy, and now they're higher in energy. So if you added energy to these reactants, the products must be higher in energy. I think number 1 is the correct diagram here. Now, is this representing an endo or exothermic process? Well, if the products are higher in energy than the reactants and they've gained energy, that means it's endothermic because energy is coming in. And that will always be true of all endothermic reactions. The products will always be higher in energy than the reactants. Now, we didn't measure the amount of energy it gained here, but you could imagine, you could say Q, or delta H, is positive 100 kilojoules. Maybe it's a positive 100 kilojoules. And that means the products would be 100 kilojoules higher in energy than the reactants. Let's try one more. All right, I think this was our other one. Let's let it run and see what happens here. Yeah, I already can see it looks like the temperature is definitely going up. Okay, so the temperature is going up in this. Now we've got to figure out what's an appropriate diagram. And this time I'm going to draw one because you might have to draw one. I'm going to put the reactant somewhere in the middle. And I'm going to put a reaction up here. What's happening here is calcium chloride is the reactant. That's the white powder. And it's dissociating into these two chemicals. Those are the products. Well, I started in the middle with my reactants because I want to think about whether the products would be higher or lower in energy. I want you to take a minute and stop the video based on what we saw with the temperature, whether you think the product should be higher or lower in energy. Okay, so here's what I'm thinking. I'm thinking the temperature is going up. That means the water is gaining energy from those chemicals. So I'm going to draw a dot to represent the chemical. I think since the temperature is going up, the water is gaining energy. From the chemical's perspective, its Q, or rather delta H, would be negative because the energy is going out. Well, if I have reactants and energy is leaving those chemicals, that means the products are going to have less energy in the end, or less potential energy, because the energy is leaving them. Now we just have to connect them, and you may have noticed on the previous diagrams that they don't get connected directly. You put a little hump in between, and we might eventually talk about what the hump is for, but you put a little hump in between it. But if you don't do that, it's not a big deal. If you just directly connect them, it's okay. And the amount of energy that these things lose is the energy from the reactants to the products. We don't even have to worry about that little hump. And so let's say that it loses negative 50 kilojoules of heat. That means that the products would be 50 kilojoules of heat with less potential energy than the reactants. And that's why the water warmed up, because that heat came out. All right, so that's an introduction to energy diagrams or enthalpy diagrams or potential energy diagrams, right? All of that stuff is the same. And you can represent how much heat is being gained or lost using these diagrams. And the key thing to remember there is that endothermic reactions always have a higher energy in the products than the reactants, and exothermic reactions, because they give off energy, they're giving away energy, they're losing energy, always have products lower in energy than the reactants.